A scientist by the name of Heisenberg, he wanted to discover the path of an electron. And so he decided to be able to do this, that he would shoot the atom with a photon. So kind of a photon probe. So shoot the photon at the atom and then look and see what happens. And from this, he knew that he needed to know both location and he needed to know the momentum of the electron. Both of those things are important to know the path of an electron. So again, this is to prove the Bohr model correct or not. So Heisenberg, he took a photon and he shot it at the electron. And when it hit the electron, he was able to determine the location. So this was discovered. But when the photon hit the electron, it changed the momentum. So the momentum was unknown. All right, so he decided to repeat his experiment a second time. So he shot a photon at the electron, and this time, I don't know if he was looking at the ricochet or what he was able to do, but he was able to determine the momentum. But when the photon hit the electron, that changed the location. So he came up with what's called the Heisenberg uncertainty principle, which means that if you know the location, then you don't know the momentum. And if you know the momentum, you don't know the location. So applying Heisenberg's uncertainty principle to the Bohr model, we find that you cannot determine the path of an electron. So again, that Bohr model is incorrect. So we like to think about those electrons going around in orbits around the atom, but it is just not proven. So that is not what's going on. So again, the more likely you are to know the location, the less likely you are to know the momentum, and vice versa. And you do need to know both of those to know the path of an electron. So a scientist by the name of Schrodinger is going to come to our rescue. So Schrodinger, he went back to the wave nature of the electron and looking at that. And he came up with his wave equation. And you don't need to know this, we'll never use it, but I do want you to notice this. So X, Y, and Z. So what Schrodinger did is he took coordinates on X, Y, and Z, so coordinates in space, and he determined the probability of finding that electron in that one place. And so every time you do the equation, if you put a dot on your graph, eventually you get a graph that looks like this. So notice it kind of looks like a cloud. And so this is how we see the electron today, that there are probability clouds. So we solve Schrodinger's equation to figure out the probability of finding that electron around the nucleus and putting the nucleus right there at the origin at 0, comma 0. Look at this graph here. So there's a 90% probability that we will find that first electron 53 picometers distance from the nucleus. And so this is for the hydrogen or the helium atom. That first energy level where you would find those 1 or 2 electrons would be this 53 picometers. Now, Schrodinger received criticism for his wave equation, because they said, you really don't know exactly where it is. And he says, you're right, but I know with a 90% probability that it will be in this area of probability. So these are called orbitals, and you can put 1 or 2 electrons in an orbital. And this orbital right here, this is our 1s orbital. And remember, you can have a 1s1 electron configuration or a 1s2 electron configuration. So again, you can put 1 or 2 electrons in this probability area. So again, electrons, they don't go around in an orbit around the nucleus. Instead, we find them in probability regions that we call orbitals. And you can put 1 or 2 electrons in an orbital. The orbitals do not have to be spherical. So this right here, this is an s orbital. So again, a 90% probability that you would find it in this region. And again, a certain distance from that nucleus, but there are lower probabilities outside that. So that's why it's kind of this fuzzy dot pattern, because it's a probability cloud. Really, it's just a math equation to figure out where it is. The orbitals do not have to be spherical. Right here we have p clouds or p orbitals. And notice that they are dumbbell shaped. So we have kind of a dumbbell around the X, Y, and Z axis. So this is called the mechanical wave view of the atom, or the quantum view of the atom. And this is how we see the atom today. So let's go through on the periodic table and address every element and show where its electrons are around the nucleus. And again, we're looking at the nucleus right here at the origin at 0, 0. All right, let's start off with hydrogen. So the electron configuration of hydrogen is 1s1. We know it has one electron and it is in an s cloud. So this s cloud is found a certain distance from the origin, and I'm trying to draw dots and my computer doesn't like it very well. But we would find it in this region around our nucleus. Okay, so this is our 1s cloud. Let's look at helium. So helium has 2 electrons, 1s2. So you would just put a second electron in this probability region. Let's go ahead and go to the next element, which is lithium. So in lithium, lithium has 3 electrons. It has 2 that are in this cloud that I've represented with black, and it also has 1 electron in a 2s cloud. So, and I'll represent that with this orange color. Okay, so it's spherical. This is where you would find that 3rd electron right here. And I'll write it in orange so you can see that. Okay, so let's go to the next element. So that is beryllium. So beryllium is 1s2, 2s2. So you would find let's go to the next element, which is beryllium. So beryllium has 2 in that first cloud, and then it has 2 in the second cloud. So just one more electron in there. All right, after beryllium, we have boron. So boron has 2 electrons, 1s2, and then it has 2 more electrons in the 2s2, and then it has 1 electron in the p cloud. So I'm going to draw this as a solid line, but it's not a solid line, it's a fuzzy line, okay? So it comes out to the second energy level, so just as much as that 2s cloud, and I have 1 electron there. Let's do the next element, carbon, 1s2, 2 electrons there, 2 electrons in the 2s2, and we have 2 electrons in that p sublevel. Now, I don't put a second electron in that first cloud that I drew. Instead, it spreads out. It's going to go into its own p cloud. And again, it comes out to that second energy level. Let's look at our next element. So we have nitrogen with 7 electrons, 1s2, 2s2, and then 2p3. So, and again, it doesn't share until it's forced to. So I'm going to have my 3rd cloud come out. All right, now after nitrogen, we have oxygen. So we have 1s2, 2s2, and we have 2p4. So you would find that that 4th p electron, it would go back to that first one that we were looking at. So I'll just color it in. Okay, so you would find it in this region. So your electrons spread out. They really don't want to share an orbital. There's a lot of repulsion to sharing, and so the atom or the electrons, they will spread out into the different p orbitals to give some distance between electrons. All right, so with fluorine, we're going to put a second electron in that p orbital, the next one. And then our last one in that series is neon. 1s2, 2 electrons there, 2s2, and then I have 2p6. So this will complete our orbitals. Now I've colored them in. Remember, these are probability regions, so not a definite like hard edge to it. So it's fuzzy. So that's why these are called electron clouds. All right, after neon, we come to our third period, and we have sodium. So sodium has 2 electrons in that 1s cloud, 2 electrons in the cloud that's just a little bit bigger that goes out to the second energy level. It has all the electrons in that p orbital, and then it has its own electron, 3s1. And so this was an s cloud, and s clouds are spherical, so they come out like this. So 1 electron there, okay, all in that region. All right, so I think chemistry is quite beautiful when you look at these probability clouds, and you can still see the energy levels. So if you're in the third energy level, then you would be 3 steps out from the nucleus. So it would, the probability cloud would be larger. So and you could continue and do this for the third period. So for the third period, let's go ahead and just jump all the way to argon. So argon has 1s2, 2s2, 2p6, 3s2, and then it has 3p6. So it has 3p electrons. So they're going to come out to that third energy level along the x, y, and then the z-axis comes straight out at us. So this is 3D, okay? And it will have 2 electrons in each one of those orbitals, okay? Well, what we've talked about the s orbital, we've drawn the p orbitals. What about those d orbitals? So those d orbitals, it actually gets really, really complicated. So these are what the d orbitals look like. So again, when you're adding electrons to the d orbitals, they will spread out. So you will put 1 electron in each of these orbitals before you make them share. So there's your d orbitals. So again, it gets a little bit complicated there. And here's your f orbitals. So their probability clouds are even more complex. And here's them all together. So again, your s orbital is the spherical shape. Your p orbital is kind of a dumbbell shaped. Your d orbital, it's like a double dumbbell, or maybe it looks like a 4-leaf clover. And then your f orbital, it looks, I kind of think most of them look like a flower. Some of them have really weird shapes, like these ones right here in the middle, okay? Here is a microscope that was able to go really small and help you to see these clouds. So we have our 1s sublevel here. So notice that there's only a spherical cloud. In our 2s, we have both an s and a p. And then in our, I shouldn't have said 2s. So here's a picture that a microscope, a high-powered microscope took. So this is your first energy level. You can see that there's only an S cloud. Here's your second energy level. You can see that there's an S cloud and then there's a P cloud. And your third energy level, you can see your S cloud. So you can see how it's spherical. You can see the P cloud. And then there's a D cloud in that third energy level. So it's that cloverleaf shape that we were talking about. All right, so if you miss class, you will have to do the lab that's in your packet. You can do it at home. You just need a pencil or a marker that you can drop from about 1 meter high. So you'll have to stand up you'll take the last page of your packet and rip it off and take that target and place it on the floor. Once you're finished with the target and you've counted all your little dots, you can throw that away. You don't have to turn it into me. But for that target that's on the floor, you're going to put your pencil right by your nose, and you'll be standing up, and you're going to drop that pencil at your target. And I want you to drop it 100 times. So you're going to get some exercise today. When you're finished, you're going to graph how many dots are in each of the areas on your target. Okay, so you have area 1, 2, 3, 4, 5, and if you are outside the circle, that's just area 6. So you're going to total that, and then you're going to graph it. So you'll be able to graph the different areas and the numbers that there are. So each of your areas, and then I want you to connect those dots, kind of a best line fit, and you should get a curve. And then answer the questions that are found in your packet.